All right, then we have transactions in a block. So again, there are blocks structure, and then there are transactions in a block, right? Transactions usually represent a smallest unit of change, right? Now the term transaction is not just limited to your Web3 world or your blockchain world. These transactions are also part of RDBMS as well, right? Where any action that you perform in your database could be interpreted as a transaction, where transitions again have the same atomic properties that we all understand. So same way, these transactions try to reduce or will try to change the world state of the system. Okay, so in a smart contract world where there is EVM, there is global state. What you're trying to change is the global state by submitting your smart contract or by invoking a function. And in typical stablecoin chain, or if we talk about Bitcoin, it is transfer of assets or transfer of coins that you're doing, right? Now the important part here is that in these stablecoins blockchains, you don't actually store the details or data or the value of the balance in a variable somewhere, right? If I ask you to create a Web2 application similar to Paytm, what you guys will do is you'll create a database, you'll create a table of users. Maybe you will create a relationship between a table of balance and a table of users, and you'll try to maintain these balances in a table there, which is going to usually store the balance of these users inside a column, right? That is how we're going to implement this. That is how usually people implement any finance solution or any solution that involves tokens or coins in a Web2 world. But with Bitcoin, you don't actually hold balances in a variable. It is an exchange of transaction, right? So you can consider it as you exchange physical currency. Okay. So let's say if I give you 20 rupees note and had to pay you 15 rupees, what you'll do is I'll hand you out 20 rupee note and you'll deduct 15 out of it and you'll return me a 5 rupee coin, right? So in blockchain, or if I talk about Bitcoin blockchain, there are two transitions that are happening. One, the transition where I am paying you, and there is a second transition that is coming back to me where you are paying me back. Okay, this is called a simple UTXO, or you can say unspent transaction output, that now I have collected. We'll talk about this in next slide, but let's go back to our data structure there and see how what is exactly held inside a typical block and a transaction. Okay, or if we can go inside, let's pick any block here. So these are latest blocks inside for Bitcoin blockchain, right? So let's take this block for an example. Right, so it has a bunch of transactions inside it. Right, now let's open a transaction in detail. Let's copy this hash and let's paste it here. I'm using JSON because it gives me much more visibility. Okay, but you guys could use any format, or you can also use a visual editor which helps you understand the transition part. So if I go back here, a transaction structure has a header, right? This typically creates a basic transaction structure. So it has a header, it has previous block address, it has a timestamp, it has a nonce, and it has a Merkel root. So this explains a block. And if we talk about a transaction structure in detail, right, you can refer from it. So it has a Merkel root, which is created from the hashes of the transactions that are stored inside it. So it has, check the size of this array. So it's a very long array, and it has quite a bunch of transactions. I think it has more than 100, and we'll keep on scrolling if I go inside the transaction. If I go in to the end of the list here, so let's check out any transition here. Let's see this part. Right, now this is a typical structure of a transition, right? It talks about V in size, and then it talks about V out size, and then it talks about total size of the transaction, and then it has fee that was involved to mine this transaction, or which was paid to the miner ultimately. And then it has block index and block height, which means the same for this chain, which talks about which block holds this transaction or stores this transaction. Okay, now this transaction involves an input and an output. That is how transaction usually happen on a stablecoin chain. Okay, so the inputs are the funds that you own. Okay, so this means a transaction that was generated for this address, right? So if I have to pay you 15 rupees, I have to have a 20 rupee note with me first, right? Or a 50 rupee note with me first. What is it? It is again a transaction that was generated for me, or which was handed out to me. Or you can imagine someone has already paid me 20 rupees. That is how I am able to pay you 15 rupees. You can imagine this way. So the transaction that is happening between you and me, the input to this transaction is the transaction where I was paid the 20 rupees, right? So that is the part of input here. Now there could be multiple inputs in a transaction. For example, let's say I had to pay you 60 rupees or let's say 40 rupees. Okay, and I have 20 rupees notes, and then I have 10 rupees. Now to pay you, let's say 45, I'll need all three of these notes, right? So you can imagine in the input section, you'll see 3 transactions here, right? And in the V out, you'll have 2 transactions only, where the party that you want to pay has the output. Okay, and then there is a address where it is coming back to me, or you can say a transaction where it is coming back to me directly. Okay, so in a lot of times you'll see that the address that is involved here is is the same address as the input. Okay, it's not usually the case, but you'll see that it is common practice. And sometimes what people do is people get confused between these addresses. Now these addresses could be generated at multiple times. So a paying address could be generated by n number of times, or you can say you can define the size or number of generating addresses as well. But for a wallet, you can generate multiple addresses for which you can receive payments on. But these wallets can ultimately be tracked down to one private key. Okay, so that is what a transaction typically contains. It has some inputs and then it has some outputs. Okay, in smart contract transactions, what you have is in general now these transactions were evolved into more complex transactions for EVM chains, or you can say for private consortiums as well, where the details inside the transaction has changed. For inputs, they provide you a read set. Okay, so let's say if you talk about an Ethereum smart contract, then it is going to have bytecodes or opcodes that are part of that transaction. That is input to that function which is being invoked. And then it has write sets, where it means the place that it needs to write to and the updated value of those sets, or you can say the updated value of the state machine or global state. We're taking an example of Bitcoin here because it is easy to understand, or you can say it sets the base of how things are managed inside the blockchain, right? Similar to why you have to read about operating system and networking, even though you aspire to be just an application developer, but still you have to understand why. Imagine you're working on a Java application and then you see when a heap size error or a paging issue. At that point, you still have to understand these concepts, heap size and paging, so that you can make sense out of these errors. Same way, once you understand these structures, these details, you will encounter more errors when or different errors when you are working on a project yourself. But these details, understanding these details and these values is going to give you confidence, or you can say some level of understanding where you can make sense out of the errors that you're facing. And what usually happens in new tech is You try to find answers, but there are very less people who are working on that part. Okay, so at that point, only your understanding of concepts can help you to make things out of or to make sense out of errors. Right, let's go back to our slides now. So what is transaction in a detail that we've seen? It has a transaction version number, which typically mentions the level of verifying, or you can say the algorithm that it is verified through. Right, these versions could evolve based on the changes or new layers that a system is going to introduce. And then there are outputs to a transaction that we saw, right? And then there are inputs to a transaction. So inputs are again unspent transactions output that you can use to create a raw transaction, and those outputs that you generated with this transaction can now be called UTXO, or unspent transaction outputs, that can be later used to create a different transaction. So that is how it creates you can say chain of transaction, and then you can drill down to the initial sets of funds, or you can say initial points of timestamp where you got the first first asset, or you can say first number of coins, or first stable coins. Right, so this slide typically explains the UTXO in blockchain. So these are again unspent transaction outputs, and they help you create transactions or raw transactions. These unspent transaction outputs can be used as inputs, and once you create a raw transaction, the transitions coming out as output are now can be used as UTXO. So they typically are assets, or you can say coins that you own, right? They have individual units. These are used as transaction inputs, also as transaction outputs. Major difference between spent and unspent is that once it has been used as an input, it becomes spent, and it cannot be used again. Okay, that is how it works. If you try to use an already spent input transaction and you try to pay someone with it, the miner is just going to reject that transaction, and now you've successfully also wasted your fee amount as well to try to fraud the system, right? So you lost the fee that you put down to miner to make that transaction successful, and also that transaction was not successful because the input that you're trying to use is not valid. They help you maintain consistency. That means they can help you maintain the integrity of the blockchain. The network checks on inputs and outputs, balances, and ensures the consistency that no one creates a new transactions out of the thin air. So that is what it tries to implement. Tries to implement a privacy layer as well. So like we just saw, you can create multiple addresses to receive an output different to what you received an input from. So you can imagine it like this: someone tried to pay you. Let's say you try to pay someone 15 rupees. So the note that you've given out is had a different serial code, and the note and the coin that you're getting back has a different serial code. Right? I'm sure the analogy is not justifying the problems here, but it can help you understand the concept. Now finally, there is consensus mechanism, which is a very wide topic, and not going to go too deep into this, but we can still talk a bit about it, and we'll try to cover more of it in the next session. So consensus mechanism helps you maintain the order in your blockchain, which means you try to incorporate a algorithm which is going to make sure that everyone stands on one decision, and the people who are trying to fraud that system could be identified with the help of consensus. Right. If I talk about POW, the race here is to solve a mathematical problem as quick as possible, right? Which usually focuses on putting down more computational energy and more computation power. Okay. The idea was here to introduce POW was to protect the system or the blockchain network from spamming. So POW is actually used in email servers as well. So if you open up your Google client or Gmail client, you'll see it there. I mean, if you inspect your browser with it, you'll see that it uses a nonce in your request, where it has to, you know, specify that basically to prevent the email servers from DDoS attacks. Same way, the blockchain network's idea to incorporate POW was to save these networks from DDoS attack. So with increase in computation power, the algorithm was designed in such a way that it is going to increase the difficulty on its own. If it's exponential increase in computation power, then the algorithm was able to correct itself with exponential computational power, increase in exponential computation power, right? So verification of things happens or of transition happens in the same way that they try to simulate the same transaction in their own storage, or you can say in their own node. And if this transition is invalid, it's going to mark it as invalid, right? Any node is going to mark it as invalid if the transition is incorrect based on the inputs that you provided, right? Now the miner being the validator of the transaction, it tries to validate that transaction, right? And it also tries to put down its you can say stamp of work, or you can say stamp of approval that I have worked this to solve this problem, and I am worthy of this much fee, right? This is again decided by the algorithm which governs the difficulty. So the rewards keep on changing, the difficulty keep on changing, right? That is again, this is a typical example of Bitcoin. If you talk about evolved chains at this point, for example, chains that are using POS, proof of staking, the idea has changed. Now there are validators which helps you validate transactions, and you don't have to put on heavy rigs now to basically rigs of GPUs and cluster of GPUs to solve hashes and to solve those problems or to work on this POW consensus. Now the race is about being the validator and staking on these assets, or you can say currencies that you can. Now if you look at the hardware constraints on the validators, right, it is also quite high compared to normal rigs or machines that we use. Now they have to do that because they expect validators to be very computer extensive so that they can solve a huge number of problems, right? Imagine them trying to solve millions of transactions. Although the TPS that a blockchain holds, it could vary, but the expectation from the machine is still there. So usually, what we see is that even to be a validator node, what they do is these public chains, they put down requirements of such that you have to have 32 GB of RAM and let's say 1 TB of storage at least. And then on CPU cores as well, they try to put limitations, or they try to put conditions that you should have at least 16 cores of CPU, which is again quite high number if you talk about normal consumer based hardware that people use, right? Usually people have 8-core CPU. Some enthusiasts have 16 or 32 cores and more number of RAMs like 64 GB of RAM, but those are very high end machines that people use. So this is now given edge towards, or the focus towards different area where GPUs are now are irrelevant, but overall specs of the machines has increased. But still, the amount of power that GPUs use, I'm sure the validators are using less power in them. So it talks about consensus in general. How does consensus work? Okay. So we just talked about how consensus work. There are a few key characteristics that I think we can talk about. So consensus usually what it tries to implement is it tries to implement limited participants or limited participations, which means consortiums or blockchains are restricted to a predefined number of groups or known or trusted parties, right? These participants are typically, let's say, organizations or mining pools, or it used to be mining pools in POW cases, or in commercial use cases, or in hybrid use cases, or in private consortium. It could be government agencies or institutions or business organizations. Then there are permission access. Now this permission you could define down again, like the example that we talked about during those discussions, that you could whitelist these addresses who are validators. That is perfect example. of whitelisting something. You can whitelist the addresses who could access or be part of these validator groups and are only allowed to validate the transactions. Right? That is called permissioned access. Or you can put down a limit on or constraint on number of stakes that a validator should have. So let's say you put down that a validator should have 100,000 coins or 100,000 ether or matic. Now only few amount of parties could even gather in that much fund, right? Which is a very huge number. That again gives you access, which is that gives you some level of restriction there, that not everyone could be validator or staker in the chain. And then there is shared control, which is again a topic which is for enterprise blockchains. So their control is decentralized among different parties or anonymous participants. Consortium blockchains maintain a degree of centralized control, where again, like we talked about, you could create some consortium members where you could assign them as admins, and then some consortium members could be validators or non-validators, which could be creating their own nodes. So these consortiums, you can imagine, these could be part of different use cases. For example, supply chain management, track and trace, financial services, right? Healthcare example, healthcare solutions, and then government solutions, for example, CBDCs. Where you could see those shared controls. All right. Yeah, so that marks the end of it. I think we've covered a lot of topics today, considering, we talked about problems in Web 2, journey of Web 3 from Web 1 to Web 2 and to Web 3, examples of Web 3, problems in Web 2, where Web 3 lags, and then we went into technical details of Web 3. And I think in upcoming sections, there are going to be more technical exercises that other people are going to take in. So yeah, I think it's going to be very interesting sessions from this point onwards, right? I think if you guys have any questions, any doubts at this point, feel free to ask.